Our project is Galaxy Image Classification. The dataset we are using, Galaxy Zhou 2, is basically the result of a program consisting of volunteers answering a decision tree of 11 questions with different number of choices. The proportion of volunteers' responses on each question is presented in a large table, which is used as our multiple targets to learn. The methods we are using is gradient boosting regression trees with certain constraints to approximate volunteers' possibility of choosing each response in each question of the decision tree. Here's the decision tree of questions. It consists of 11 questions and 37 response choices for us to approximate.
Color could represent energy generated by different physics procedures. Thus, it is representative of the shape of galaxies, and red galaxies tend to be round, while spiral galaxies are more likely to be. We calculate the Laplacian of the image and the distraction of the blurred image and the original image. It is far brighter than the surrounding area, so we can enhance the contrast of the image and retain only the brightest region, calculate the ratio of the parameter and area. To measure it, we calculate the distance of gradients in horizontal and vertical direction. Last distance means the galaxy is more likely to be viewed edge-on. We transform the color images to binary images with auto threshold, then draw lines from the center and count how many times the intensity changes along it. If the count is larger than 1, there is a spiral arm in this direction. Repeat this method in all directions to count the number of spiral arms.
In this part, we rotated the processed image to different angles, found the angle that makes the rotated image most similar to the original image, and recorded the difference. We used OSTU threshold to transform the original image into binary image and further optimize the image with erode open and close operation. Then we rotated image 72, 90, 120, and 180 degree respectively. To calculate the difference, we subtracted the original image from the rotated image and calculated the proportion of the remaining part to the whole image. We recorded the angle that lead to the least proportion and the corresponding proportion as features.
The whole contour of a target galaxy, excluding noise, is really necessary. Although it can represent strong visual feature, it is also hard to extract because visual feature we want to obtain exists only in one specific instance within the image, the galaxy located in the center. So before directly finding contours of the image, we have to first somehow detect the target galaxy, extract a relatively complete shape of it, and then do contour detection. The trained image gave us a really strong condition that the target galaxy is located at the center of the image. So the only thing we need to do is to separate the target galaxy from other galaxies, which can be brighter or darker and larger or smaller than the target. Here, the method I use is one of the algorithms for image segmentation called watershed. The first step is to generate histogram for each image. The top image is the histograms of 17 random galaxy image. We can easily observe the pattern for each histogram. So if we sum everything from 0 to 250, we can get such a curve in the bottom. So I utilize histogram of each image to the thresholding. Why is this good? We don't have to set a constant value in order to do thresholding for each image. Here is the result. After thresholding, the top image is generated with a higher threshold, which is used as shear foreground for watershed. The bottom image is generated with a lower threshold used as a shear background. And I use connect component method to label the top image. After watershed, we can actually get a bunch of contours, so we have to choose the best fit for the target galaxy. Here I'm going to organize the contours in a tree structure. In this example, these contours all have one parent node, but the leftmost image is a contour of two galaxies, so I prune the tree to get rid of the left contour. After that, for every leaf node, we calculate the Euclidean distance, choose the best fit. Here are the results. For the intensity concentration, I use an intuitive method. I simply increase the radius from the center of galaxy, calculate the sum of intensity in the window, and compare with the sum of whole galaxy's intensity. The top and the bottom image are two results for blue and red channels. The white points in the image represent radii given different percentage of light intensity. The red channel, which is described in the bottom image, have a brighter bulge feature, so the radii are relatively short.
The idea of gradient boosting trees is to use many base learners, namely small decision trees, to approximate the residuals of previous model. After training the model, we use constraints observed from the decision tree of questions to constrain our predicted results. Finally, we evaluated our model using RMSE, namely root mean squared error. The result value we got is 0.12.